In our final section of this chapter, we're going to review the concept of graphing linear functions, and we're going to start working with the idea of function notation and what do the graphs of linear functions look like and how are they similar and different. So key vocabulary is you need to know what function notation is, what is a family of functions, and what is a parent function in general, but the parent linear function in particular. Okay, so function notation basically involves taking y, so you'll see here we have y, and replacing it with f of x. Okay, so you can think of this as the value of function f at the value of x, which would be a different value of x for each different time we might evaluate the function. Or what we generally say is we call it f of x. It does not mean f times x. The f is not part of the equation. We have just replaced y with the term f of x, and partly because you can use the function notation for a variety of things. One, you can tell a person what to plug in to the function by putting that number in the parentheses. So if I, for instance, say f of 2, that means to plug 2 in place of x. Okay, and also if we're working with multiple functions in the same problem, I can tell the difference between the functions because one of them is maybe the f function, and the other one could be the g function, and another one the h function, and that way we can tell them apart. Okay, so if we simply want to go ahead and solve for the function for a given value like I talked about up here, if I wanted to find q of negative 4, so you'll see what they've given me is that q of x is negative 8 minus 32, and then they want me to find the value of this function when x is negative 4. So in function notation, the way I would write that is q of negative 4 is going to be 8 times negative 4 minus 32. 8 times negative 4 is negative 32 minus 32, and that's going to equal negative 64. So I know that q of negative 4 is equal to negative 64, but my q sure looked like a g, didn't it? Let's try that again. Q of negative 4 is equal to negative 64. Okay, so it isn't that what we do has changed, but the way we're writing it has changed a little bit, and the way we're talking about it has changed a little bit. If we take a look at another problem, the gray wolf population in central Idaho has been monitored for several years for a project aimed at boosting the number of wolves. And the number of wolves can be modeled by the function f of x is equal to 37x plus 7, where x is the number of years since 1995. So if I want to graph this, I'm going to go ahead and put some axes in. Again, we're not going to look backwards in time, and we're not going to deal with negative wolves. Those things aren't going to really exist. But if we take a look at this starting point, the 0 point, that represents the year 1995. And then this direction would be the number of years since 1995. So this would be 96, 97, 98, 99. But on our graph, they're going to be 1, 2, 3, 4, 5, etc. Okay, so that's what we're modeling with this particular equation. If I want to go ahead and write this out as function notation, which we've got there, f of x is equal to 37x plus 7, I know that 7 is my y-intercept, so 1, 2, 3, 4, 5, 6, 7. There's the y-intercept. And for each year I go, I'm going to go up 37. So this is going to be a problem the way I've scaled the graph. So let's take a look at how can we scale the graph a little better. Maybe it would be better if I did, I'm going to try every 2 being 5, 10, 15, 20, 25, 30, 35, 40, 45. So Up here at the top, I'm at 45. That's not so bad. So 7 then would be right about here. And then I'm going to go 37. So when x is 1, I'll have f of 1 would be 37 times 1 plus 7. That would be 44. So 5, 10, 15, 20, 44 is right below that. So right here, this is what the graph looks like. And you see it got really big really quick. So I may have wanted to go back and adjust my scale again to make this a little easier. But you get the idea, and I don't need to go back and do that. The domain of the function consists of all the values of x for which the function is defined. So that means x has to be greater than or equal to 0, because I know what it is 0 years from 1995, it's 7. And I'm only going forward in time. Backwards in time would be before this program was put in place, and the function for that period of time might be much, much different than this. And then when we look at the range, which would be all the values, the y values in this case, or the output values, the smallest it could be is 7, so I know that y is greater than or equal to 7. Okay, so I've graphed the function and I've identified its domain and range. Linear functions are what's called a family of functions. So it's a group of functions with similar characteristics. So functions in this form, y is equal to mx plus b, or f of x is equal to mx plus b, those are the same thing, constitute the family of linear functions. And later we'll work with the family of quadratic functions. And you'll work with the family of cubic functions in other classes, etc., etc. But they all have a basic core form that can be expressed in its simplest form. So when we talk about the parent linear function, it's the equation in the simplest form possible. And in this case, it's with a slope that's 1 and a y-intercept that is 0. Okay, so you'll notice that this is also very similar to the direct variation model. In fact, direct variation models are all part of this family of linear functions, if the variation is a linear variation. Okay, so if you take a look at this parent function, you'll see it has a slope of 1. I go up 1 over 1. And it has a y-intercept of 0. This is what the parent function looks like. Every other function in this family of functions is an alteration to this parent, can be looked at as an alteration to this parent function, something we've changed about the parent function. So if we take a look at some graphs here, I'm going to graph these other graphs. This is the parent function, y is equal to x, right? The red line, that's what that is. And if I want to graph these other functions, here I have a y-intercept of -3, 1, 2, 3, and also a slope of 1, so I'd go up 1 over 1. That gives me my second point, and I could graph that. And in fact, this is parallel, right? It's parallel because it has the same slope. The difference is each point along the way, it's 3 lower. So this is what's called shifted down, right? So this is the parent function that has been shifted downward. Okay, when you look at this function, my y-intercept is 5, 1, 2, 3, 4, 5. But my slope is different. It's a -3/2. So if I go down 3, 1, 2, 3, and right 2, that would give me a point. I could also go up 1, 2, 3, and left 2. Both of those are the slope -3/2. And I go ahead and graph this. Now you'll notice that it's very different. It's not that the slopes are the same and it's just been shifted down, other things have happened. So if we look here at this y-intercept, you can see that it's been shifted up, but then also my line has been rotated off to the left. So this has experienced an upward shift plus a rotation to the left. Right? And if you look at this last function, the y-intercept is the same, but the slope is different, -7/2, 1, 2, 3, 4, 5, 6, 7, and over 2. And like I said before, I can go up 7, left 2, 1, 2, 3, 4, 5, 6, 7, and left 2. And then we can go ahead and graph that one. Let me just adjust it over to be closer to where it belongs. About there. And you can see it hasn't been shifted up or down. This one has just been rotated to the left. Now you could look at it as rotated to the right as well. I just think of it, when I think of going from positive slope to negative slope, I happen to think of it as rotating to the left. Okay, that doesn't make me right. It's just to sort of sum everything up. When we're looking at the graphs of linear functions, right, we've got parallel lines. Again, we have the parent function here, right? The parent function is here, and we can have graphs that have the same slope as the parent function or parallel to the parent function. We have graphs that have the same y-intercept as the parent function, but different slopes, but they're different positive slopes. And here, different negative slopes, different slopes that are negative slopes. Okay, one last little application problem. A cable company charges new customers $40 for installation and $60 per month for its service. So my function of x will be equal to $60 per month times the number of months plus the $40 installation fee. Okay, to attract new customers, they reduce the installation fee to $5. So then the new graph, g of x, is equal to 60x plus 5. If I graph both functions, how will they be related? So again, let's put in some axes here so we can work with this. And I see that in this case, I'm going to do tens, 10, 20, 30, 40, that's 40. 50, 60, 70, 80, 90, 100, 110, 120. And then in this direction, we're just going to look at number of months. So I'm just going to 1, 2, 3, 4, 5. So this is months. This is dollars. I see that my y-intercept here is 40. That's right there. And I know that for every month I'm going to go up 60, so that would be up to 100 here. And this is what my graph is going to look like. And if we take a look at the other guy, I'm going to start at 5. So this was 10, so I'm down here is where 5 is. And as I go 1 over, it's also going to go up 60. So it's 50, 65. It's right there. And if we look at that graph, you'll notice that our slopes are the same. So we have parallel lines. It's just the G graph is related to F by being shifted down by how much? 35. Okay, that's the relationship here. right? And that's the final section for this chapter.